All right, so today we definitely will start with a new lecture topic, but before that, let's do a little bit of reminders and also some recap from last time. All right, you're programming assignment number 1. I think I definitely should really get started, even though you still have some days before the due date, but you really want to get some struggle, pinpoint exactly you need help, and then reach out to either the TA or myself. You know my office hour pretty well. And the contact information for the TA, you can go to the common eClass site to really find their information. You can reach out to any one of them. And this one will be exciting. So we already spoke about split array problem last time. I'm going to do some very quick recap about the lessons we have learned from that example there. And either tomorrow or over the weekend, most likely tomorrow, I'm going to give you guys an extended version of this problem here. That's going to be harder. I think that will also help you think a little bit more about recursion in general. And of course, it's going to be helping you for the programming test as well. All right, I'll release that to you. And then as for the solution for this problem here, I'm thinking about different possibilities. We'll see which one we might go for. Either I will just release the source code to you. You can, the solution code to you. You can take a look. Or we can, I can record some short tutorial video to go over the solution with you. Or we can host a live session over Zoom, and then I can go over the solution. We'll see which one might work better for you, right? But at least you gotta try first, all right? Most likely tomorrow. Any question about the course in general before we do some recap? All right. All right, so from last time, we basically just solved a single problem, which is not trivial. So we talk about that split array problem. So you can think about that one there is a very good example about what you're going to deal with during the programming test. So you really want to take a look at the format. You will be given some informal description about the problem, and you will be given some example calls to the method, and they might be expressed in this form, or most likely some JUnit test cases for you to start with. And the insight that we talk about, which is the recursive lines you have to write in Java, is quite brief, no more than 10 lines. But the way things are going to work out in terms of a runtime execution, you have to watch out for how things should be traced. I think that's very important. We talk about several times of tracing the code. We talk about build a tree from scratch. We did it together. Make sure you know how to do it. And we talk about how to use a call stack briefly so you can see the order of execution for the method. And also, most importantly, you want to watch out for how to do this in Eclipse using debugger, step into and step over. So these are very nice resources for me to make up questions for your written test and exam. Right? I want to make sure you learn those stuff. They're good stuff about recursion in general. And we also talk about the short circuit evaluation, which you guys kind of learned from the previous courses, but make sure you brush up about the meaning for short circuit evaluation. Okay? And I think that's about it. And we also concluded with this particular general tree structure. I promise I'm going to revisit this one more formally and more systematically. We're going to talk about tree and its mathematical properties very thoroughly after the reading week. But I just want you guys to remember one thing. If given this particular structure here, you want to calculate what's the total number of method calls in this entire execution. You can see level 0, we got 1. Level 1 here, we got 2. And this level here, we got 4. And all the way to 2 to the power of 7. That is the sum of some geometrical sequence. You may even recall the formula from that, right? So this will be something you have to know for the final exam, right? But I just want to give you a little bit preview. So knowing some mathematical property about a tree is very useful for understanding not just data structure, but also tracing your program in general. All right, so that's basically what we spoke about last time. Any question about the split array? All right, if no, you can look forward to the harder version, which I'm going to give you guys for exercise. For a little bit struggling, okay? You really got to struggle before you can grow tomorrow, okay? Okay, let's now talk about the new lecture. All right, you can already see the slides on the lecture site. Just in case you already downloaded the slides, since I already made it available on Tuesday, I make some important updates, some polishment about the slide just today before the morning class. So if you can please just re-download it just in case you want to look at that during the class today. All right, let's now talk about this lecture here. And let's start with what does it really mean for asymptotic. That simply means we are considering input size not just like a 0, 1, or even within 1 million. We're talking about input size very large towards the limits basically, right? That's really what asymptotic really means. And it's a prerequisite for you guys to already have studied 1019. You have seen some big O notation already. I would say the breakthrough you're gonna have to, the breakthrough of thinking you have to do for this course is to see how you can apply the mathematical analysis skill about big O into algorithm, right? That's a connection we have to make. Not too much today. Today I need to do quite a bit of scaffolding, some introductory stuff, but starting from next Tuesday, you will see lots of examples about applying mathematical analysis to coding, right? So you really want to have a very nice marriage between math and also programming. We'll get there. All right, so this slide here, just to remind you, here we are basically going to analyze Java code, but for your programming assignment, make sure you know how to use debugger, right? Just a reminder. For those of you who don't really know how to use the debugger, I cannot emphasize more. It's going to be your best friend during the assignments period and also programming test. During the programming test, nobody can help you. Maybe debugger will be your best friend. Okay, you're going to look at the resources if needed, or reach out to me. I can show you how to use the debugger. All right, that's good. All right, so what should we learn in this lecture? So I'm going to revisit the terminology about algorithm, data structure, and some additional terms. And then I will try to do some one page, like a summary about all the terms we're going to talk about today. And it will be nice for you to integrate those terms into your daily vocabulary whenever you talk about software development, right? You want to learn about what people talk about in general or in the industry. Try to be professional. And we're going to talk about how you can measure how good the algorithm is. We're going to talk about different criteria. We'll get there. And also efficiency, right? So efficiency, what kind of efficiency can we define? Are we talking about more about speed, or are we talking more about space? And we'll talk about what kind of measurement can you make. So I'm going to start with some very short account about experimental measurement that's very intuitive. It might be something you have to do sometimes anyway, just to get some insight or quick intuition about the if you want to compare different algorithms. But the ultimate solution will be something that's theoretical, using your knowledge from 1019. But I'm going to go over from scratch. I'm going to have to show you again about the definition for big O. Not today, but Tuesday. And especially, I want you to make sure you understand about the limitations of experimental measurement. That's something very important to pick up. So we will have some very good motivation to really go for something mathematical. And asymptotic, I just mentioned. All right, so by the end of hopefully next Tuesday or Thursday, once we complete the lecture, you want to be very clear whenever we say, given two algorithms solving the same problem. What does it really mean? When we say the two of them are equally efficient asymptotically. Or what does it really mean when we say one is more efficient than the other asymptotically? That is very important to really know exactly what we mean by that. Okay. All right, so in this course, we only focus on the upper bound. We don't really talk too much about lower bound or tight bound. That will be something maybe you will learn a little bit more in 3101, the algorithm course following this one here. More upper bound for this course. All right, let's now revisit some terms and also define some new ones very quickly. Okay. So data structure is really a way to systematically organize your data. So whenever we talk about data in our programming context, attributes, right, in Java, right? Because every attribute is more like a variable. Variable, integer, Boolean, reference, they are data. You want to somehow talk about accessing, just read only, or about making some updates, right? You want to think about these kind of different operations you may perform on your data. So that's about data structure. We're going to see different ways of doing that. Think about array. It's like a one data structure. The way to really get access to an array is by supplying some index into the array. That's valid, right? And very important for this point here, so whatever data structure we're going to introduce, you always have to remember there is not a single data structure that's going to work well, always. Otherwise, there's no point of studying this course. We can just teach you one, right, in the first or second year. So there will be so many data structure we have to learn, and you have to make an informed decision about where, when to use which. Okay, so strength and limitations. Especially when we start talking about linked list, you have to be very clear about the strength and limitation between arrays and linked lists. That's for later. And computational problem. So in order to define an algorithm, you better know what the problem is you're trying to solve. Right? So we say well-defined. So well-defined here simply means you must have the input. What's the input? For example, input can be an array, or it can be maybe array plus another integer, right? You got to define exactly what the input is. So user of your algorithm, they can pass the correct input. And also, what's the corresponding correct output given the input? So computational problem here simply means you want to describe exactly the input and output relationship that you want to supply. Any detail that's to do with computational thinking about coding, it will be left to you as a programmer. Just one example. The input could be, let's say, a sequence, which can be a list, it can be an array. So we simply got an array of n elements. So we're just starting from index 1 all the way to index n. So here, n is a very important concept as well. So this tells you the input size may be different. When n is equal to 0, we got empty array. When n is equal to 10, we got 10 elements in the array. When n is 1 million, we got 1 million elements in the array. Right? So n here is a variable that's going to impact the running time very much, as we'll see. And the output here, so we simply say, let's, if we can make some sense out of this description. We say the output is going to be a permutation or reordering of the input over here. It's still going to be an element there, but it's such that A1 less than or equal to A2 less than all the way to AN. So what kind of problem are we solving here? Quite obvious. Sorting, exactly, thank you, right? So you guys want to really get used to, just given the input and output, you have to somehow design the steps and algorithm accordingly, right? Just some example. You can think about each test case, like given a particular input, we call that an instance of the problem, okay? A particular input, right? Or test case, all right? All right, an algorithm. Algorithm is going to be the solution to some well-specified computational problem. Right? Given the problem, you want to decide the algorithm for that. Of course, each problem might be solved by different algorithm. You have to decide which one might go, for example, depending on their running time. And it's going to be a sequence of computational steps. So here, we're emphasizing about sequential nature. So we don't talk about anything that's going to be executed in parallel. We don't talk about it, right? Just sequential. Make it simple. You got maybe 10 lines of code. You're going to execute starting from line number 1 all the way down to line number 10, one by one. If there's any method call in between, you branch out, right? And then come back, like using a call stack. All right, it's going to take some input and then output. The last point here is important. Okay, hopefully you can see that. So each algorithm is going to manipulate some chosen data structure, right? So here I'm using plural, meaning that for the more sophisticated the algorithm is, the more data structure you may have to use. You may not use just a single data structure. You may have to use multiple data structures. You got to choose which one might be the best for your algorithm. You might use a tree, you might use a hash table, etc. All right, pretty straightforward definition. So I'm going to go over maybe a few more slides. We'll see many terms, and then I'll try to summarize them, kind of draw some relationship between them in a single page. Okay, let's go over a few more slides. How do we measure how good an algorithm is? Correctness is no compromise, the number one priority. If you cannot even achieve correctness, don't even think about, don't even discuss efficiency. Correctness, most important thing. To the least extent, you should really get something that's correct and terminates. That'll be enough. And then you think about how to make it faster. Always think about if you can produce the expected output. That's what really correctness means. And in this course, we're going to talk. We basically are going to exercise again about how you can use the unit and regression testing, which you guys learned from 2030, right? Using the JUnits testing framework. That will be correctness. Just make sure you get a green bar at the end of your developments. All right, assuming that your program or your algorithm is correct, and then we can now start talking about efficiency. All right, just remember, always go for correctness first and then efficiency. There are two things we can try to judge. One would be about, here I say processor time over here. I'm more talking about the very intuitive notion about how fast your algorithm is. Let's say I'm using this very old Mac over here to run my algorithm. It might take, for example, 10 milliseconds to execute some sorting algorithm. Maybe using one of your better Mac machine, it might take just 1 millisecond, right? So that's really about the processor time I'm talking about, okay? The absolute processor time, okay? And we'll try to make this a little bit more abstract, a little bit more platform independent later. Time complexity. And the space complexity is something that's also very important, don't get me wrong. But in this course, we don't focus too much on the space efficiency. It's important, but maybe later, once we get to 3101, you may talk about memorization, dynamic programming, then you might talk more about how much memory you can save, but not in this course. That's a little bit too advanced. But whenever there's any memory concern, I will let you know explicitly. So we're going to focus more for this course about time complexity. And correctness, no compromise under any circumstances. Okay, efficiency, we gotta focus more on the time. All right. Okay, a little bit more, and they'll do summary. The time, so storage about today, storage is pretty cheap, so that's why we don't really focus too much in the first instance. Unless maybe you have to program for some embedded system where the memory is pretty small. In that case, maybe memory is something you have to tweak, okay, but not our scenario. All right, solution must be as fast as possible. For now, just understand it as if I can get something that will run 10 milliseconds, it's definitely better than 11 milliseconds or even 20 milliseconds, right? Things like that. As fast as possible. All right, so the running time here is going to depend on input factors. So whenever you want to really test your algorithm, you want to consider two things that are important, okay? One will be about the size. That's very intuitive. So let's say you want to test how efficient your sorting algorithm is. You shouldn't only test for 0 elements, like an empty array. Well, you should take no time. Or maybe you only got 10 elements in the array to sort. Maybe you got 1 million or you got 2 million. You got to stress test your algorithm, right? So that's about the size. You really want to make sure your algorithm will always terminate within some reasonable time by some very large input. Of course, how large the input is also depends on the application scenario, right? All right, the second thing is about structure. That's something even more important. Let's say I'm talking about sorting. If I give you something that's already sorted, it shouldn't take too long for that to be sorted, right, by applying the sorting algorithm. If I give you something that's hardly or never, it's not sorted at all, it might take a little bit longer. Right? So that's what I meant by structure. So it's really hard to characterize the structure in general. We're going to see case by case, but we'll see later. Okay. All right, so how do we determine the running time of the algorithm, right? So let's go a little bit more and more specific. So we're going to focus on the timing efficiency. So there are two approaches, and we're going to focus on one of them just for today. And we'll do the more rigorous one starting from next Tuesday. We're going to first talk about measure using some experiments. You're simply just trying to implement the algorithm, run it on some computer, and record how much time it will take. Right? That's something I will show to you. I'll show you the whole process as a complete example. And then we're going to identify limitations about this approach, and then we're going to move on to something that's more mathematical, which is what you learned in 1019. All right? Any questions so far? All right, we have seen many terms so far. Why don't we do a little bit of quick summary, just about putting everything together. All right, quickly. All right, let's now start from scratch. Okay, let me just make sure. Good. All right, so what we got is, let me see. I don't quite like this guy here. Can I get rid of it? There we go. Good. All right, so let's now start with some algorithm. So think about the algorithm itself is more like a black box to the user, algorithm. All right, and most importantly, algorithm should be with respect to some computational problem that's already defined. So the algorithm is really meant to solve some computational problem. And I'm going to put a computational problem here. Computational problem. And as we said on the slides, in order to define a computational problem, you have to specify, given the input, what will be the corresponding output. So this one here would be, you got some input, and also what will be the expected output. All right. And let's talk about just from the public point of view. From the user's point of view, they only need to be bothered by the input and output. They don't need to be bothered by exactly what's the internal workings for the algorithm. For you, as the implementer, or the programmer, or the engineer, you will worry. Okay, we'll worry about that in a moment. So from the user's point of view, they're going to pass the input and output. So we got some input here. And also we got some output here. And both of them should really conform to what's really defined in the computational problem. For example, let's say sorting. If we got a sorting problem, the input and output should both be an array. In that case, the input here must be an array. Output here must be an array as well, according to the problem. Right? All right, so let's put it here. So input is going to conform to what's defined in the computational problem. Output is also, it will conform to it. The format, the types. Conforms to in terms of the type. Right? If you declare that to be an array, or if you declare that to be an integer or an object, etc. For both the input and the output. All right, let's now talk more about inside the algorithm. It's more like a black box. Right? From the user's point of view, it's more like a black box. All right, so we got two things inside. We got a sequential composition of the steps, basically lines of code. I'll just say steps. And these steps are going to manipulate on some chosen data structure. So there will be certain data structure which you will declare as variables or whatever. So I'll say DS, data structures. And plural, you may use more than one data structure in your algorithm. You may. Actually, very likely. Okay. And then the steps is going to manipulate. For example, let's say if you choose to use a tree as a data structure for your algorithm, what can be the manipulation? You might say, I want to start with creating an empty tree, and then I want to keep adding elements into the tree, and then I want to somehow keep extracting and removing some element from the tree. By the way, what I just described is about heap sort. That's something we'll get into at the end of the course. All right? But for now, just understand what manipulation really means. You just basically try to kind of access or update the data structure that you have chosen. Okay. All right, so that's about the algorithm and the computational problem. And we talk about how we can judge the goodness of the algorithm. So let me draw another line here. So judge by. All right, so two criteria. Number one, correctness. No compromise, okay? And as for correctness, I'm gonna give you guys two ideas over here. Only one of them is gonna be used in this course. Another one is more like a put you in perspective, okay? The one we're gonna use is called testing. JUnit testing, for example. And people usually call this the dynamic approach. Dynamic in the sense that you have to fully implement the algorithm using some programming language, make sure it compiles, and then you have to run this and test the input and output during the runtime. That's why it's dynamic. Another approach, I'll just mention that for your information. Of course, as opposed to dynamic, it will be static. Okay? The other static approach is called formal method. And this approach over here is going to depend on what you guys learn in 1090 about discrete mathematics, set theory, predicate logic. Okay? For those of you who are in the software engineering stream or software development stream, the course that you're going to take later, 3342 and 4315, they are the courses to address this aspect. It's much more advanced than testing, but it's going to be very valuable. For example, Amazon actually use formal methods. Well, some real way company in France also use formal method. Okay, but that's for later. For this course, you just focus on testing. But for your knowledge, there's also something that can be done statically without even running the code at the runtime. All right, so that's about correctness. And let's talk about efficiency. Also to judge. We can also judge by efficiency here. And for efficiency, we got also two aspects. Either we got the time or we got the space. Let me talk about space here. Not much to say. We don't really focus on that, but doesn't really mean it's not important. So you want to remember the space may impact the running time as well, which we'll see some example today. Okay, they may impact the time. So whenever you say I say RT, that means running time, like a time efficiency. Okay, it's an acronym I'm going to use pretty often. And as to measure the time efficiency, so there are two approaches. Okay, 1 and 2. One will be experiments, which we're gonna see first, and the other one will be mathematical function. More specifically, the big O notation, which I will review from scratch on Tuesday. All right, so these two approaches. And as for the experiments, before I talk about its limitation, we're gonna see some example first before we can appreciate what a limitation might be. Okay, experiments over here. Okay, that's something I'll revisit the summary page in a moment. Okay. All right, that's just a quick summary about the 3 slides that we went over, right? Just to kind of connect everything together, right? Okay, so let's now go back here and move on with the slides. Oh, sorry, I just got myself confused. Beg your pardon. There we go. Okay. All right, so let's now talk about experiments. And the idea is very simple. Basically, you want to make sure your algorithm is fully implemented, let's say in Java, any programming language. So that's executable on some computer. And then we're going to pass down input and also of different sizes and structure. In general, you have to consider both the size and the structure. But for the particular problem we're going to solve together using experiments, sizes will be enough to focus. But structure you should also worry about in general. Okay. Okay, this is something we're gonna make sure we measure. Elapsed time. That means we're really calculating the physical time it's gonna take to run the algorithm from the beginning until termination. And in Java, we have a system class library, and we can simply measure what's the current time in milliseconds. If you ever use the method here, you will know what I'm talking about. If no, you can feel free to give it a try. Very handy method to really measure. Idea is very simple. Think about the one I'm highlighting over here is about some method call, where the method being called is actually the algorithm you have implemented. So we are saying that we're going to measure what's the start time of the algorithm and what's the end time of the algorithm. And then calculate the gap. So that'll be the elapsed time. All right? So the elapsed time, which we also call absolute time, is a number. Now we realize measuring the absolute time has many limitations. So we would rather have something that's more relative for comparison. That's something we'll focus on more from Tuesday. Okay? But let's now talk about this one here, right? Just for completeness. And you're going to measure the running time. Maybe you got 2 algorithms to really compare which one you should really choose. You kind of measure the elapsed time for one, you measure the elapsed time for the other, for various input sizes and structure. Ultimately, you have to somehow present the result to somebody about your design decision or implementation decision. So you're going to visualize it, right? For those of you who ever seen machine learning project, they like to doing visualization, right? There's some visualization library in Python, for example, right? So visualization is a very crucial step. which I'm going to show you some example as well, simple ones. All right, so this one here is to say, at the end, once you plot the graph for running time, you also have to make some claim to say, okay, based on the input I've tried, now I'm going to choose algorithm number 1, for example. But in order for your claim to be sound and solid, you got to make sure all the inputs you have tried on the experiment, they should be, I put in quote, complete. Okay, complete in the sense that you should have already considered as many input scenarios as possible. Okay, I'll give you some example. What should be reasonable and what should be unreasonable. And let's say we want to do experiment about some sorting algorithm, right? It would be very unreasonable if you say my claim is based on some experiment just on empty array, or maybe some very small size array, or maybe some array that's not exactly, that's basically almost sorted, right? It's not very solid evidence to show. On the other hand, if all the input you have really used to really run the experiment, they are pretty large size array, and also they are kind of randomized about the structure. So that way you can claim more soundly about the which one is more efficient, right? Pretty straightforward stuff. All right, any questions so far before we see the actual experiments? All right, let's now see some example. Okay, so this is the problem that we are trying to do some experiment about. And then I'll present to you 2 different algorithms of solving that in Java. Let's say the input here, well, I talk about computational problems, so I gotta give you the input and also the output. The input is 2 inputs. We got character C, which can be any ASCII character that can be typed from your keyboard, for example, like a star. And then there will be some integer. Let's assume it's a positive integer. Okay, let's assume. N can be 1, can be 200, can be 400, etc. And the output is going to be just another string. And that one there is going to repeat the character C for n times. As simple as that. All right, so for example, let's say if you give a star and also 15, you're going to output star repeating 15 times as a string. Okay, that's a problem. As you can see, the structure of the input doesn't quite matter in this case because you're repeating the character. So we're going to focus more on the sizes of the input. All right, let's see. Let me now give you guys maybe 2 algorithms over here. All right. I'll give you some quick focus over here, and then you guys can stare at the code for maybe just a few moments, and then tell me which one you think is more efficient. This one here is basically make sure whenever you want to do a repeat of the character, you use the concatenation character for string, like a plus, right? That's already predefined in Java. On the other hand, here, in order to have another repetition, we're going to call a method called append from a library class called string builder. Okay? And other than that, other than the yellow highlights I just showed to you, the structure of the 2 algorithms look basically identical. Okay, just one more moment. You guys can take a guess which one is more efficient. Yeah, go ahead.
String builder.
String builder? Okay, that's actually correct answer, but why would you think that's more efficient?
Because the string class in Java, every time you append to it, it reallocates the memory every time, whereas the string builder does it in a more efficient way.
Yeah, that's pretty good, pretty good. Okay, your fellow student was pretty much said what I want to say, but I'm going to repeat it anyway. So algorithm number 2 turns out to be more efficient in terms of time. We'll see the actual running. I'm going to summarize the result in a table for you. Okay, let's now take a look. I'll give you guys some intuition since I'm talking about this example. It's kind of good to know. Over here. All right. So we got algorithm. Oh, sorry. Over here. Yep. So we got algorithm number 1 and also number 2. Algorithm number 1 is using the concatenation operator for string in Java. So here you can think about this can be rewritten as answer equals answer plus C. That's what plus equal really mean, right? So we can visualize like that. In the beginning of each iteration for the loop, right? You see this loop over here. Answer will be just pointing to some string. And the way you can think about string is like an array of character. Let's say this is the repetition we have got so far. In order to update the new string by another character at the end, the way to do it, like what your fellow students said accurately, you actually have to, first of all, allocate a memory, another array, that's going to be exactly one element longer. That one there is going to take the extra character C. At the same time, you're going to maybe run another loop yourself to actually copy this part here into this part over here. That's how you create another repetition that's longer, one character longer. After that, you're just going to reassign answer from here into here. Right? As you can see, within each iteration, you're going to run another loop. That's not very efficient. Right? It's going to waste the space for sure. Also, it's going to waste the time by copying the contents. All right? So that's the critical insight. On the other hand, for this guy over here, okay, I would not dive too much into the details, but you can think about conceptually, if I got answers already here, over here, if I already got this, somehow they will be able to just add one extra space into it without having to do some explicit copy. Okay? And I can just mention something here. That's something we might get a chance either to get some reference to it, or maybe I'll talk about it. They will have something called doubling strategy to actually handle it. And that one turns out to be will take just constant amount of time to really do it. So there will be nothing like you have to copy whatever you have got so far, which can be very big, to make the new string. Okay, so you don't need to do that. All right. Again, we don't need to dive into details for doubling strategy for now, but you can look it up just for now. All right, having the intuition about these two, so we know that the ultimate winner should be algorithm number 2. All right, but let's see exactly how we can run the experiments, right? Let's see that. Okay. All right, this table here is actually going to summarize the result for this for the experiment. So I want there are 3 columns here. This column here, N, is about input size. This is how we're going to organize. We're going to start with certain starting input size, and then every time we go into a new row, we're going to double the input size. And the idea will be, we want to see every time you double the input size, how is the running time for string concatenation going to increase? And also how the string builder append algorithm is going to increase. We're going to observe some pattern from there. Okay. Row number 1. If I got 50,000 repetitions to make for a character, it will take about 3,000 milliseconds. Not too bad. Versus 1 milliseconds. So string builder, you can see already is faster if you look at the numbers. But just if you talk about 3,000 milliseconds, 1 millisecond, we cannot really tell seriously, right? Might be okay. Let's now double the input size from 50,000 into 100,000. If we do that, you can see now, observe the pattern. Roughly speaking, it's about 3 times, right? You can see go from almost like a 2,000 to maybe 7,000, about 3 times or 2 times around that range. And the running time here for string builder doesn't change. Okay, let's push further, right? 200,000 repetition. And we go from here to here. It's about 5 times more, all right? And this one here from 1 to 2, about 2 times. Right? You can kind of see the idea here, right? So this will be something very important for you to observe if you want to run experiments, as opposed to doing just paper analysis. If you keep going until the end, I'm going to show to you, until we got something here. Let's say for this particular input size, right? It will take 3 days for string concatenation, as opposed to 135 milliseconds. All right, you can see who the winner, which one should be the winner. All right, and of course after this we'll see the visualization like a plot next slide. But it's important for you to make the following observation. As I said, every time you want to go from one row to the other, the input size will double. And roughly speaking, you can also verify yourself, the string concatenation running time will increase about 5 times. You can double check, right? And for string builder, it will increase about 2 times, roughly, okay? Linear. If you look at on the paper over here, we definitely should really choose repeat number 1 if we have to repeat that many times. But if your goal is really to repeat maybe up to, for example, let's say 50,000 times, in that way, it doesn't matter which one you choose, right? So you really want to think about which one will be the application scenario, okay? If you look at the plot, that's really going to be like that, right? So this one is going to be higher, so that will be repeat number 1 using string concatenation. And this one here, the blue one, is the string builder. As far as the absolute running time is concerned, we may choose the string builder, that's lower. However, once we get to the lecture on Tuesday about asymptotic analysis, these two algorithms will be considered equally efficient asymptotically. All right, we'll get there. All right, you can revisit this particular experiment and come back here and kind of ask yourself why. Okay, if I remember next Tuesday, I will mention that briefly, but not for now. Okay. All right, any questions so far? That's just about a story for experiment, just for you to get some idea, right? If you want to run experiments as opposed to analysis, that's what you got to do. And let's now gradually move to the second approach, which will be on some mathematical analysis. But we need to understand what the challenges are for the experiments. There are 3 things I'll summarize over here, and I'll go back to the summary page just to make it a little bit more complete. The number 1 here is very important. In order to do experiments, it is required for the program to be runnable on the machine. But think about it in this way, you are reaching a dilemma. Usually you want to do experiment just to see which algorithm should I choose. And whenever you want to think about which algorithm to really choose, you don't necessarily have to implement it fully. What you could have done is to just document the critical steps of the algorithm and figure out the running time, rather than fully implementing it. So having to fully implement the algorithm, each one of them, in some programming language, is really a waste of time before you can make an informed decision. Right? So that's number 1 drawback. So it would be very nice if we can somehow just make a decision about which alternative we want to really choose by just having some analysis on the paper. That would be very beneficial, right? That's something we'll do. Can there be some higher level analysis to really determine this? Yes, there will be. What people like to do usually to specify algorithm for analysis on the paper is something called pseudocode. But we don't do pseudocode. Pseudocode to me personally is too informal. If you allow yourself to express your algorithm in an informal notation, then you can easily confuse yourself. So in this course, we're still going to use Java code, but we can have some tolerances. For example, if you miss some semicolon, if you got slightly wrong about indentation or brackets, it's okay, as long as you can express your idea well. But I think we're going to stick to Java. That's what I would, that's what I will stick to during the lecture as well. All right, so drawback number 2. Okay, this is also important. In order for you to compare algorithm number 1, algorithm number 2, you got to make sure everything else, the condition is equal. You got to make sure they were implemented in the same programming language, you're using the same version of compiler, and also you are running them on the same OS, the OS version, etc. Everything got to be the same. Otherwise, you're not doing fair comparison. Right? That one does not sound as that one is not as easy as it sounds. You got to make sure every parameters there for your experiments are equal for the algorithm. All right, so I'm just giving you some idea about hardware and software, right? That's a second drawback for experimental analysis. And number 3, this is also one possible drawback for paper analysis. I should really make it clear. But this one here is easier for you to actually make some missing cases whenever you do experiments, because maybe you're just too excited about plotting the visualization, but you maybe haven't really considered some important input scenario. But when we do paper analysis, we always focus on worst case scenario, so we really get right to the point. Okay, so it's less easy like a less easier for us to make such a mistake when we do paper analysis. All right, so number 3 is about you may have some missing, maybe you're not really considering worst case, maybe you're simply missing some important structure of the input. All right, so that's really the 3 drawbacks. All right, let's now just go back to the summary page quickly, and then I'll put these 3 down. So we talk about experiments. Okay, experiments over here, so I'll put star here. So the 3 limitations that we spoke about, right? Okay, number 1 is about you are required to have a full and also working implementation of your algorithm. Especially, you want to get something that's 100% working. It's not that trivial. It will take you some time before you can even make a decision, right? You got to be very, very cautious about this step over here, working. Okay, number 2, it's about the execution environments. You got to make sure they are exactly equal when you do the comparison. So execution environments. All right, number 3, it will be about the input if you really consider all the possible scenarios. So it's about representativeness of your input. Representativeness. All right, so these are the 3 drawbacks. And if we move on to paper analysis, we are not going to suffer from these 3, right? So just make sure you can understand why we don't really do experiments per se in this course. There's a reason for that, right? All right, any question so far? All right, that's good. Let me go over a few more slides, just mention a little bit more concept, and then we're going to talk about how we can do things on the paper. And then we'll take a short break before we do some examples, some definition together. Okay, just bear with me, a few more slides. How do we move beyond experimental analysis? We want to analyze efficiency, about time, running time. So there should be some high-level description. We're going to stick to Java, okay, for our analysis purposes. And also, we want to make sure we are going to measure relative efficiency. We're not so much concerned about the absolute running time. Should it be 10 milliseconds, 100 milliseconds? Not our concern. More about relative. Okay, you will appreciate more about relative maybe next lecture. Okay, but for today, you just got to know about. We're going to talk about relative. And whenever you talk about relative efficiency, it's not going to depend on the execution environments. OS, language doesn't really matter, okay? Relative. And also, especially consider worst case scenario. Okay, so this will be the flow, okay? So for today, after the break, I'm gonna first of all define what primitive operations really mean. There will be an explicit checklist for us to really follow, okay? I'll do that first, and then we're gonna do one example together about counting primitive operation. And when I say counting, I really meant counting precisely, all right? You gotta be precise. And then next time, Tuesday, I'm gonna talk about how we can somehow generalize about a primitive operation into some mathematical function. That's what we'll do. All right, and then we talk about worst case, especially big O. All right, so today we're gonna mainly just focus on number 1. Okay. All right, so why don't we take a short break by taking attendance? Okay. Okay, so before the break, we spoke about how you can run experiments to measure the absolute running time. So now we are moving towards how you can do relative measurement. And the idea will be just to start with, we're gonna see how we can count primitive operation. I'll define what primitive operations really are, and then we're going to do some example together, some full example from scratch. Okay, let's now define. So a primitive operation simply means it's a very low-level basic instruction that's going to be executed, and doesn't matter which platform you're going to use. It's just going to take a constant amount of execution time. For example, maybe you want to load something from the memory, or you want to maybe write something to the memory. And that one, it's not going to make a huge difference between different platforms, right? That's what we call primitive operation. It just takes very little time, constant. All right, let's now go through some list. So variable assignments will be a primitive operation. You basically just want to go to some memory location and update the address, right? Update the location with some value. All right, so whenever you see some variable assignments, it's going to be a primitive operation. And also, if you want to index into an array, let's say I want, given an array, I want to go to index I. So for those of you who already took 2031 or 2032, you know that in order to get to some index of the array, just calculate what's the offset of the address, right, from location I, and then go there. So pretty efficient operation. So indexing into an array is also a primitive operation. And also arithmetic, relational logical operation will also be primitive. So here, one example here. You can see the plus here is arithmetic. Plus, minus, multiply, divide, or modulo the percentage sign operation. It will also be arithmetic. And also relational operation, larger than, less than, equal, etc. Okay? And also the logical operation that we spoke about last time, you know, the and the or operator, they will also be constant, also primitive operation. All right, so far, hopefully that makes sense. And then, so this one here, since we talk about OO, right? Of course, if you talk about the efficiency for like a C itself is not OO, but C does have like a record, so you may have something very similar to access some field in the record. But if you talk about purely procedural language, maybe you don't have the dot notation. But since we talk about OO, like a Java in this course, so what about if you want to get access to some attributes? Right, so this one here is going to be also primitive operation. But you might be wondering, what if I got multiple dots in the notation, right? I might say A dot B dot C and etc. Right, so that's something we may also want to clarify quickly. Okay. All right, since we talk about OO, so we got to talk about like access to your attributes. And there is something you guys learned back in 2030 called aggregation. Rings the bell somehow? Okay, let's talk about it quickly, right? And then I'm going to talk about some very important assumption we have to make. So we talk about accessing and objects attributes. And let me sketch maybe the idea a little bit more abstractly, but you will get an idea. Okay, let's say, and this is something we call aggregation back in the 2030. So somehow we can use the dot notation to navigate between the classes. Let's say we got 3 classes over here. We got class number 1, we got class number 2, and we got class number 3. Oh, show better. Okay, we got 3 classes over here. All right, let's call that A, B, and C. So let's say we got class A, and also we got class B, and also we got class C. Very typical. Of course, you know, in the more complicated application, you might get hundreds of classes, which is also very normal. Okay. Let's say in class A, we declare some attributes of type B. Meaning that using B here, we can navigate to class B, because B here matches the B here, right? That's what we learned earlier. Okay, and then let's say in class B, we got C type attribute called C. And also here we got A, and also just call it A. Okay, so let's say these are the attributes set up for us. And let's talk about, let's say we got a one method here in A called MA method. And in the context over here, we may have some dot notation that's kind of long, right? For example, we may write, for example, just B, which is referring to B here. Or we may write B dot C, right? In which case, we're going to navigate to this class. We might say B dot C dot A, etc., right? So these are all valid expressions, all right? So you might be thinking, the dot notation here, as long as it's valid, we may have arbitrarily long dot notation. So wouldn't that be counted as not primitive operation? You might be having that confusion. which is okay, right? So we're gonna make the following assumption, which is very reasonable. So in any reasonable software application, like with OO methodology apply, normally the length of the dot notation, like a number of dots you're gonna use, should not be more than 5 or more than 10, even that. It's like a very fixed constant. If you actually got, in your application, you got a dot notation with 100 even, there's some problem with your application, all right? So the assumption we are making is really the following. Okay, I'm gonna write it down and I'll explain a little bit further. Important assumption. First of all, let me say the dot notation here can be arbitrarily long as it's valid. As long as it's valid. However, we're going to make the following assumption, which is the length of the dot notation expression is always a small constant. As I said, it should not be more than 5, for example, right? Small constant. And more importantly, when I say it's a small constant, that's something I'm going to write down, and you will appreciate this wording I'm going to say a little bit more, maybe next time. The small constant means it does not depend on the input size. And typically, the input size could be like a collection of certain size, like an array of size n. If the dot notation depends on the input size, then there'll be another story. But it's never the case. So that's why we're making that assumption. Okay? Small constant, that means it does not depend on the input size. Typically, just n. For example, array. Okay? All right, that's important for you guys to know. Okay, we're just making the assumption that attribute access is really a primitive operation. Okay, let me go back. Okay, also, if you want to do the return statements, that's also a primitive operation. Have you seen I missed one thing from the list? What about method call? It should be very common, right? If you want to reuse certain block of code that you declare as a helper method, what if I call a helper method? Can I say calling a helper method is always a primitive operation? Or should I say it's always a non-primitive operation? Doesn't sound either is true, right? How should I phrase it then? Huh? Depends on the method. I like that. That's exactly right. It really depends on the method. So whenever that's why I don't really include it in over here. Whenever you're making a method call, you cannot make any judgment right away without looking into deeply what that method is about. Maybe that method there is very simple. It would be considered primitive operation. Maybe that method there itself will do some sorting. In that case, it may not be efficient. All right. So I'm going to summarize this point very quickly, right? And then we'll do one example. Okay. I want to leave enough time for us to think that example. Okay. Very quickly. Okay. So here, I will definitely revisit this idea very, maybe again. Oh, let me make sure I switch. Okay. Whenever you got a method call, okay, so the idea will be may or may not be a primitive operation. May or may not, really depends. Okay, PO, primitive operation. So let's say if I say obj.n, where the n over here, the method being called should be considered as a primitive operation, really depends. Okay, so case number one. Okay, so now case number one would be, let's say n should be considered as a primitive operation. I'll give you some conceptual sketch. Consider as primitive operation. Okay, let's say n looks something like this. Maybe it has certain line, variable assignment, array indexing, some if conditional, very simple ones. And then over here, you got something maybe a little bit more complicated, right? So you can think about here, each one of them could be some obviously primitive operation that's already defined in our list, right? A primitive operation. And over here, there are two cases which we're going to see more example. I want to list them just for today. Can be, number one, it can be another method call. But that method call turns out to be like a cheap operation. It doesn't involve any like expensive computation. Okay, just another method call. Method call that actually consider a primitive operation. So this point here is very important. The level of number, how deep the method call change should be really depends on your application. So you really have to do some deep analysis to figure out, right? And number two, you might got some misconception that whenever you got loops, that means it's expensive. Not necessarily, okay? So here I'm gonna give you some idea, and then we'll see some concrete example. So if you got a loop with a fixed number of iterations, then it's not considered as non-primitive. For example, the number 2 over here, I'll put it here. Okay, number 2 here. Let's say I got a nested loop. You might think nested loop is very bad. Not necessarily. I might say for integer I would be 0, and then I less than 99, and then I plus plus. And then I got another for loop here. Integer j will be 0, and j less than 99, and then j plus plus, right? You can see it's a double nested loop. But overall, how many iterations do we have? 100 times 100. 10,000. Not bad, because it's fixed. It does not depend on input size. Anything that does not depend on input size is what we consider as primitive, right? So that's something you want to remember, all right? Okay, so here, fixed, also not dependent on some input size. Okay, all right, case number 2. So for case number 2, it will be the case where m is considered as primitive. Beg your pardon, it's when m is considered not as primitive. And not primitive operation. All right, so that one there could be m here. For example, m itself has a loop. And then I say int I equals 0, but now it's going to be bounded by not a fixed number. It's going to be bounded by maybe some array size n. I can say maybe I less than a.length, and then I plus plus, right? Let's say it contains a loop like this. In that way, you can see this will be the size of the input. So if you consider this loop over here and this loop here, their nature are very, very different. This loop over here always going to execute for exactly this number of times. No surprise. It's always fixed. On the other hand, this one here, depending on how large the array is. If the array goes towards infinity, then this method here will also goes towards infinity. All right? All right, so that's good for now, just to get some idea about what we really mean by it depends on the method call. Okay. All right, it's a method called primitive operation, depends. All right, we just talked about it. So the running time of algorithm, we're now going to approximate it by counting exactly the number of primitive operation without worrying about what is the execution environments. All right, let's now do one example. I got about 12 minutes. Should be good. All right, I want you guys to look at this fragment of code, which is going to take some input array, and then it's going to find out the maximum. I'm pretty sure you know how to do it, right? That's maybe more like a first year level. And I'm going to switch to a different page with the same code, and I want you guys to think about two questions, which I'm going to ask you. All right, so the same fragment of code over here, and by the way, this input parameter arguably is redundant, but just a little bit easier for our analysis. You can think about the way we're going to call the method would be, I might say find max. I got some input array A, for example. And then I'm just going to pass A.length always. So just a little bit easier. So whenever we talk about analysis, we can refer to n, just easier, rather than A.length, okay? All right, you guys look at the code, and then at the same time, I want you to think about two questions. Question number 1. Line number 3, we got this Boolean condition. How many times exactly will that be evaluated? If you got answer, hold it, okay? Also, the line number 4, 5, and 6 is considered as the body of the loop. How many times exactly is the body of the loop going to be executed? And we're now counting. So if the answer should be 5, for example, if your answer is 4 or 6, wrong. Got to be precise. Okay, I'll give you guys maybe 1 minute, to really take a look. And these two questions are very important to answer first whenever you got this type of accounting question. But we'll see something more sophisticated maybe on Tuesday. But let's start with this one here today. Okay, hopefully you guys got some answer. All right, question 1. How many times will the Boolean condition I less than n be executed? I heard n here. Anybody else? Any other answer?
Depends on the input size.
Okay, depends on input x.
Size.
Well, the input size is n.
Yeah.
Right, so it's already there, right? So you say n. Anyone else? N minus 1? N minus 2, interesting.
N minus 2.
N minus 2. Okay, I like. Anybody who would think n plus 1? Just for completeness. Huh? Would you change your answer to n minus 1?
Yeah.
That's okay, it's okay to change. Would you like to change?
Yeah.
Okay, so it seems like you guys think n minus 1, right? Sorry, wrong. The answer is n. Sorry,
Okay.
you got it wrong. You got it right actually in the beginning, but now you change it. Okay, turns out it's only n. All right. All right. Let's now figure out why it's n, which is going to be fundamental. So guys, do you remember this condition here is so-called a state condition for the for loop, meaning that as long as this condition here is true, we're going to keep executing the body of the loop. As soon as it becomes false, we're going to exit from the loop. All right. So now think about this. Let's do a little bit tracing. I initially is going to be 1, and I less than n. All right? So we can expect that. So let's say n could be something very large. Let's think about in general. So we are going to see a pattern like this. I is going to take such values for as many times as necessary to make I less than n true. So we can stay in the loop for as long as necessary. As soon as I becomes large enough, since we got I++ at the end, it's going to become false for just one time, and that will be it. All right? So that means maybe when I is equal to 1, it's going to evaluate to false. When it is equal to false, all the way to what will be the last value that's going to make it false? Sorry, I really meant to say true. True? True. So what will be the last value that's going to make it true? N minus 1, right? N minus 1 is the last value that's going to be strictly less than n. All right? And then after the last increment, we're going to get n, which is going to make it false. All right? Hopefully you can see this pattern here. So we are basically saying all these value for I is going to make the condition over here simply just true. And the very last value here is going to make it false. And how many values are there? N. N minus 1 plus 1. So we got n. All right? So the answer to the first question there, it should be n times. And to be more precise, n minus 1 times where I less than n is going to evaluate to true. And also 1 time I less than n is going to be evaluated to false. All right? The first question is very important. All right? What about second question? N minus 1, good, right? That's, as long as it's true, then it should be good. All right? N minus 1. So what we should do now, we are now ready. We already answered the trickiest question for this problem here. And now we're going to calculate, count the primitive operation line by line. And of course, you don't count the header. Don't do that. All right? We're going to start from line number 2. All right? All right, for line number 2, how many primitive operation do we have? 2? Which 2? Equal, which is variable assignment, and also array indexing, right? So 2 of them. Very good. So we're going to get variable assignments and also array indexing. Okay, we got exactly 2. Okay. And this is particularly outside the loop. So that's why we don't have to worry about any of question 1 or 2 just yet. Okay, we can skip a little bit. You can see line number 7 is also outside the loop, right? How many primitive operations do we need to execute? 1, right? Just 1. On the other hand, just for your information, if I change this one here to change that into something like AI, for example, it would be 2 instead, right? Array indexing plus the return, okay? Just for your information. So only 1. So that one will be just the return. And that one there will be just 1. So far we have calculated 2 plus 1, 3. Now let's talk about the loop itself. Okay. So now we're going to focus on this one over here. Okay. Now what about this one here? How many exactly? This might be the trickiest one. Because here we got this guy here. Also we got our friend here. N plus 1 sounds interesting. What do you mean? N for sure, because here we are going to execute this condition here n times. Each time, how many primitive operation will be involved? Just 1, because it's a relational operation. All right, good. So for this one over here, it's going to be, okay, let me write it down precisely. It's going to be n minus, just n times 1. Okay, that would be a little bit better for you, right? Think about the n over here is about question number 1. All right, that's all we figure out. And also the 1 over here is about the relational operation that we have over here. So n times 1. On the other hand, let's say, hypothetically, if I change this condition here to be something like I less than n or I larger than 0. In that way, it should be n times 1, 2, and 3. See my idea? All right, good. We'll see more things like that. All right. So this part here will be n. How about this one here? How many times? 1, right? Only initialize 1. Okay. So this one here is just 1. So you will get n plus 1. Just for line number 3. We're talking about when we try to execute the code, how many primitive operation will end up being executed. Okay, we got 3 minutes. We can finish that. And this if condition is going to be checked every time. Now, how many? N minus 1 times. All right, so n minus 1, first of all, because we know the body of the loop is going to be executed n minus 1 time. So this one here, first of all, we start with n minus 1 because of this. And each time, we're going to do array indexing. And also, we're going to do the relational operation. So n minus 1 times 2. All right? And here's an important tip for you to remember. When you try to calculate the precise primitive operation, you don't have to focus much on the logic of the loop. Because you might be thinking, this line number 5 here might be conditional. Because it will only be executed if the if branch over here is true. So for now, you just assume that it's true for every iteration. That's something we can assume, all right? So now, what about this one? How many primitive operations will end up being executed? This one here. N minus 1, I agree. That will be the number of times for body of the loop. 2. 1 here, 1 here, right? Thank you. And what about the final guy here? Well, this guy here, right? Of course, I would suggest be a little bit more cautious, right? We know that this one corresponds to I equals I plus 1, right? So now, first of all, it's going to be n minus 1 iterations for each iteration equal n plus times 2, right? So what we're going to do is we're going to do the following math. Don't get this last step wrong. Add all these together. All right, so let me show to you. Everything I've said here has been said on the slide as well. So let's go over the slide. So these are the 2 questions we kind of answer. And then we got to go line by line. You can also take a look. Eventually, you're going to add up all these lines together and all these. And what you will get is something like a 7n minus 2. All right, I got 30 seconds. Let me just make a conclusion. What does 7n minus 2 really mean? So the n here is about the size of the input array. If array size is 1, that means we can have 7 times 1 minus 2. That'll be 5 primitive operations being executed. If we got n being 10 elements in the array, that will be 7 times 10 minus 2. We got 68, right? So you can plug in the number to see. Right, so that's something we'll need to continue to practice with more advanced example. Okay, I'll see you next week.